So our menu for day 9, it's the last day I'm going to be bothering you with my teaching, so no more homework, I guess, unless Professor Ali wants to give you something. Um, yeah. So today we're going to look at what methods, I want to give you, I found a nice figure that really shows an overview of what kind of methods you have to compute multiphase flow. Okay. And this can be a very wide area, really depending on what you want to calculate. Remember, basically what we want to calculate, what we are focused on is dp dx. But I will give you some examples that there are some people interested in something else. Okay, so maybe, it depends. You need to have a method suitable for what you want. Then we're going to talk about the drift flux model. That is a model that is using average properties, treats the multiphase like an average. Okay? Some emergency in the computer. I hope it's not going to explode, no? This message will self-destroy in 5, 4, then we have to run. That treats the multiphase like a mixture with average properties. And that's the method you're going to use here in class. Hmm? And then we will see, remember, to calculate pressure drop, we have to change from local from standard to local. And we will see how you do that with the black oil properties. And unfortunately, we won't have time to talk about compositional. How do you do it when you have a compositional model? But black oil is what, the workhorse of the industry, what everyone is using. So I think it's going to be more useful if we talk about black oil than if we talk about composition. And then we have an exercise. Then we have this pressure integration. I will describe more or less how it is done. And then we have an exercise, and then we have final comments and end, okay, of these 2 weeks. So let's start about which approaches, and we basically have 2 approaches to study multiphase flow. Okay, basically we have one approach that is mainly empirical. That means basically you go to the lab and you run a lot of experiments, and then you define some very interesting value, usually based on a dimensional numbers or some sort of a dimensional number. And then you plot the data and you try to find trends. Okay, this is very highly empirical. You don't have much physics behind it, but you're just trying to recognize trends and design like correlation behind the trend. Like, this what we have done last class with this method, this correlation by this guy. There is some physics, but very little physics behind this expression. Okay, where that expression came from? This expression, well, it has a dimensional numbers. It's kind of balancing, one effect or the other, but at the end it came out from, best fitting of data. And then we have another approach that you have to remember. That word is called mechanistic, empirical, and also mechanistic. That is based on, basically what you do is you use all the equations. So you use a mass balance, and then you use momentum balance, and then you use energy balance. But the thing is that it might be, at the end, this system of equations that you get, that you have to solve, it might be very complex. So you have to insert, to squeeze in some correlation, okay, some experimental correlation, to explain for parameters that you really don't know how to model, okay, or the modeling is too complicated. So, but this one, if you see, this one is completely empirical. This is all based on experiments. While this one has experiments only in some aspects. All the others is using equations. And it's basically This approach basically uses considers the flow pattern that you have. Okay. So the distribution of the phases. Okay. And remember, we are basically in this course, we are interested mainly in dp/dx. Okay, that is our main goal. But people might have different, different. For example, um, they want to know in transportation lines. Okay, how much if you're going to get, you know, if you're going to get water, there is a very severe problem that you have water condensation or water accumulation at the top, and then you get corrosion. It's called top of line corrosion. Okay. You have emulsion, for example, emulsion, oil, water emulsion. You have, you want to know, for example, liquid accumulation and slugging. Okay. Remember what liquid, okay, if you have a pipe, something like this, the liquid will start to accumulate and then it will block the pipe, and then you have all of a sudden a flush of liquid that goes out. And then you might have, for example, sand erosion, a hydrate formation, and wax, etc. Okay, you have many particular distinct problems that people want to study, and depending on that, your model will be more or less complex. Okay, in this course, we're focusing basically on this problem. Okay, we want to know the pressure drop because that's going to affect the performance of my system, the production of my system. But you have different models; they are so complex as you want. So there is a nice figure. This is a paper by a guy called Shippen and Bailey, and I think it was published in 2012. And they show this figure, and I thought was very interesting, so you can see. So it splits basically all models that we have. First, you have time here in the y in the x-axis, and on y you have like the categories. Okay, you have models that are completely empirical, some models that you start to recognize that there is something called sleep, but you still don't recognize flow regime. Then you have models that actually account for both, for flow regime and sleep, but they are still empirical. And then you have the mechanistic models. They have some sort of a force balance in them. So I think it's not the point to go through each one of these models and you show, if you need in your professional life, you will go and you say, well, we think for our case, this is the best. So that's the one you use. Or you try different to see which one works better. What we are now currently, you see what happened with time. Initially, no sleep, no flow regime. You had some very simple models, and actually here you have something saying for how many phases does it apply, oil and gas, oil, gas, or water, inclination angle. Yeah, and that's all I think. If it goes from vertical, that means vertical, and when it's on the side, it means horizontal, and when it's down, it means, the downwards flow. And this is still some Baxendale and Thomas, some correlation that is found in commercial software. This Hagedorn and Brown is also found, sorry, and Findlay, Gray, all of these are found in, and all of these are basically the correlations that we call for for calculating pressure drop. Okay, And then you have some more advanced models that basically they try to put some physics, they try to use some force balance or to use some momentum and mass balance and solve it simultaneously. And then you see you have the commercial simulator basically that we have for multiphase flow. We have Olga, we have Leda, we have Schlumberger. That's what the pipe sim has, and we have one called Tulsa, the unified flow model of Tulsa. Okay, and here you have some other things. So initially, up to this point, everything was steady state. Then came Olga, and basically we enter into the age of transit. Okay, and that's something I want to discuss with you a little bit. Is to say that multiphase flow. If you look, for example, at bubble flow, okay, if we have these bubbles, and let's say that you are looking at this point, okay, you put here a meter. Basically, the volume fraction of gas divided by the volume fraction of liquid in that is going to be actually a function of time. It's going to change. You got bubble, no bubble, bubble, no bubble. Okay? So the point here is that multiphase is always transient, always. Okay? If you try to put the finger someplace, it will surely change. Okay? But the thing is that if we make an average over a period of time and it doesn't change the average value, then we can consider like if it's a steady state. Okay? So we have like two ways. We have steady state that, keep it in mind, is not really steady state, but actually it's an average steady state, okay, an average in a period of time. For example, you might have people that they are very interested how the droplet moves in the column and how it moves. So for that case, you cannot use steady state. You have to use a transient model that actually looks at the droplet and see how it moves through the column. Okay. For us, we are looking at the scale. We don't want to look at this small scale of, it depends where you're standing. We have a scale of maybe millisecond, then second, then minute, then hour, then we have day, then we have week, month, and then maybe we have year. So maybe there is some transient happening at this scale, millisecond and second, but we are basically concerned when it comes to minute, hour, okay, around that period. We don't want to look more in detail to how does it change. And then you have another approach that is a transient, that you actually want to look at how the variations are, and they are actually in the range for petroleum applications, in the range from second all the way maybe to hour. Okay? And that's, for example, relevant here. An example is slug flow. This slugging. For us, we are going to stay here. Okay, and the methods that we are going to discuss now, it's basically just assuming steady state. But just keep that in mind that really is not exactly steady state. Things change. Okay, but in average, if you make an average over a period of time and you make an average also in the cross section, you will see maybe that the holdup, okay, for example, if you plot here in this section, okay, you plot this void fraction versus time, you will see that maybe it has some variation, but the variation is very, okay, it oscillates very little around that. Okay, if you have, for example, a variation that does something like this, then you have to go for a transient model. Okay, but if you have a small variation and you know this is happening because you have bubbles entering and coming out, then you use steady state. Hmm? Okay, so now let's talk about the main model we are going to use here. So it's like the drift flux model. And this model considers only one momentum equation for the mixture, okay, using average properties. And then we say that dp dl or dp dx is equal to minus, so comes exactly like we do for single phase, okay, similar to single phase. So we have, in single phase we had the friction factor, and now we're going to call it the friction factor for two phase, okay. Then we had the density. In single phase we had density of single phase, now we have two phase. Then we have the velocity, also two phase squared over 2 diameter, minus density two phase, the sine of theta times g, minus the velocity of two phase times db two phase over dl. Okay, and then we have the density missing here. Yes. Okay, so I did the same. I just took the same equation, exactly the same, and then just starting to put everything will be two phase. Okay, and here, so the way we're going to use this model, okay, and there are different variations. The way we're going to use it here in class, we will say that if the density of two phase is going to be equal to the void fraction times the density of the gas plus 1 minus the void fraction, the density of the liquid. Okay, and this one will be the slip. Okay, if you use the slip here, then you will have is an homogeneous model. Okay, if non-slip, how do you call the non-slip epsilon? If lambda g, remember, is used, then this is called the homogeneous model, because you are assuming that both phases travel at the same speed. Then is the homogeneous model. Okay, keep that in mind. And we're going to use like a very simple approximation. We will say, well, basically the velocity in two phase is going to be equal to the velocity of the mixture. Okay, and the velocity of the mixture is equal to liquid plus gas, right? And we are going to say that basically this term over L is approximately equal to 0, or is very small compared to the rest. Okay, so we can neglect this guy here. Okay, maybe because neglecting, for example, a fluid expansion in the segment and change of, we assume there is no change in the cross section area. Okay, and then we end up with this expression. That's what we're going to use in our exercise today, and that's a very simple model, but still can give you a very powerful BT squared over 2 phi minus GP. Okay, we end up with that with that. Okay, so now let's talk about, how. So how is the procedure? Okay, how is the pressure to calculate? If you have the pressure at the wellhead, how do you calculate the pressure at the bottom hole? Or if you have the pressure at the bottom hole, how do you calculate the pressure at the wellhead? So it's called pressure integration procedure or steady state multiphase flow in well bores. So you start, if we have a point, the first step is to start from the point with pressure known. Okay? It can be, if you're doing bottom hole equilibrium, then the wellhead pressure will be known, and if you're doing wellhead equilibrium, then the bottom hole pressure will be known. Okay, so you start with that point. Then, uh, then you have to compute. Okay, with P and T, you compute the local rate of oil and gas. Okay, QO and QG, and you also compute all properties and compute all fluid properties. That means, what do we need? Like using this correlation that we used yesterday, okay, you need 8 things. So you need density of oil, density of gas, viscosity of oil, viscosity of gas. You need the interfacial tension, oil and gas. What else do you need? I don't think you need anything else, right? These are the main things. Yes, and then you use, so using, here you compute superficial velocities on that point, on that point. That means QO over density of over cross-section area, USO, and USG, Q gas over cross-section area. And then after we do that, okay, you see the first one, local rates, properties, superficial velocities, and now comes the dPdL. Okay, now comes compute pressure gradient at that particular point. Okay, so dPdL you compute, and here you can use this method that we're going to use here in class. Okay, that is like a drift flux. You can use a mechanistic model. You can use an empirical model. You can go even to your multiphase expert, and then you say, please give me this delta P for this point, to any multiphase expert you have. Okay, and after we have that, then it's like we have, okay, then we have to discretize the tubing. Okay, discretize the the length or the tubing in segments. Okay, then we say, for example, we have, okay, P1, P2, P3, P4. Okay, and then you have to integrate. And to integrate, remember, basically what we have is like a differential equation. Okay, we have integrate numerically the differential equation dP over dL is equal to a number. Okay, and then you have that P at a certain condition set, it can be, the TVD. Let's say, that we have, let's assume here that we have wellhead pressure. Okay, P at wellhead pressure at 0, TVD equals 0 is known. Okay, and this is a very simple differential equation that you can use any method that you want. Okay, you can use an explicit integration method. Okay, like for example Euler, or you can use Runge-Kutta. Okay, You have different methods that they allow you to solve that differential equation. Okay, Euler, Runge-Kutta, etc. Or you can use an implicit integration. Okay, and this implicit requires some iteration inside because you assume a pressure, then you compute the gradient, and then again you see if the pressure that you assume is the pressure that you have, and you repeat. Okay, we are going to use here in this class, we're going to use Euler. That Euler basically tells you that just P, how did we call it here? P4 is equal to P wellhead minus dP over dL evaluated at the wellhead times delta L. Okay, yes, and that's delta L. Okay, just very simple. Just we take the gradient, multiply it times the distance, and then sum it up to the point that we already have. Okay, and then we move down. Okay, that's one method, Euler explicit. You can use all kind of methods, any method that you want. Remember this method? What was the main warning that your teacher gave you when you had your course in numerical method? You need a lot of intervals. Okay, the delta L should be very, very small. Okay, for Euler, like here is a warning. Okay, Euler is very nice, very easy to integrate, very simple, but the problem is you need a very small interval. Euler requires very small interval. Okay, and then we have again another point. Then we have P4. Okay, and then we move now to P3, and we do exactly the same. Repeat from the beginning. Yes? Okay, so again, I have pressure, I have temperature, I have to calculate the local rate, I have to calculate properties, then I have to compute superficial velocities, then I have to go to an expert that will give me what is the gradient, okay, using different models. And then I have to, actually, I don't have to discretize, okay, so discretize, that might be the first step. That should be done from before. Okay, so that will be step 1, and this we call it step 2. And then we use any method that you want. You will see you can use Runge-Kutta, fourth order. You can use, how do you call this? Well, you can use any method that you want. And then you at the end, you're going to find out P3. And then you move to P2, P1, etc. Okay? And this is also, this approach assumes that T is given. Okay? The temperature distribution is given. If you don't have temperature, it becomes a bit more complex, and I don't want to discuss it here. But we are assuming that the temperature we have somehow. We have the temperature of the fluid at the wellhead, the temperature of the fluid at the reservoir, and we can just make, for example, an interpolation. Hmm? Yes. So before doing an exercise, there is something that we need. We need to compute. We need to compute QO and QG from QO and QG, right? We need something that will allow me to convert between these two. And I told you that if you have for single phase for single phase gas, it was just QG equal to BG times Q of the gas, right? And for undersaturated oil, it was just Q Q oil equal to BO times QO. Okay, but when we have a mixture, it's not so simple. Okay, so I'm going just to show you how is the conversion. Okay, with, and I think this is a very generic way to represent that transformation. Okay, so you create, this is using black oil, this is using black oil tables. Okay, using black oil. Okay, and this is if you have local rates and you want to compute standard condition rate. And this is if you have standard condition rate and you want to so actually this is the one I need. Let me see if we can just take this one away. Okay, and you have all the parameters we have discussed before. Okay, we have, so let's see. So here you see you have a matrix and you know how to multiply. How do you multiply a matrix times a vector? Is this row by this column, right? So it's this one times this one, this one times this one times this one, yes, and so forth. This one times this one, plus this one times this one, plus this one times this one. That gives you this number, and so forth. Okay, now we're going to simplify. But let's see first what is the definition of all of these things that we have here. So if we take, okay, a container, okay, with, let's say it has both, okay, because now we are not dealing only with gas or only with oil. We are dealing actually with both phases. We want something that will be generic no matter which phase I have. And I have here a certain volume of oil and certain volume of gas at, this is at any pressure and temperature. And I'm going to take it to the surface, okay? And I'm going to take it to P standard conditions and T standard conditions. Okay, somehow that's also something that is very here. I have a process, okay, and we are not going to discuss too much about it, but here we have a process. It can be I just take the container and put it at a different pressure, but sometimes I have a series of separators or I have something else. Okay, so I have a process, and here I find, for example, I have a bigger container with maybe less oil but with a huge amount of gas. Okay, and here I have a V gas at standard conditions and BO at standard conditions. Okay, so I define by definition BO at a given pressure and temperature is equal to the volume of the oil at that pressure and temperature divided by the volume of oil at standard conditions. Okay, it's a ratio between this guy here and this guy here. Hmm? Now Bg is equal to volume of gas at local P and T, and B of gas at standard conditions. Okay. Now there is something that I didn't let's make it here. When you hmm, yes, let's see how we do it. So when you vaporize, so when you, something that we forgot, okay, when you vaporize, um, yeah, let's leave it like that. I think to avoid confusion. Okay, and Rs is equal to volume of gas at standard conditions, okay, divided by volume of oil at standard conditions. Okay, Those are the three that we're going to use, and you see here we have a small rs. We're going to assume that small rs is equal to 0. Okay, for now, for this development. So we don't care about rs. We don't make any distinction. Okay, and these are the three variables that we have, and the matrix is simplified to qg is equal to bg times qg, okay, minus bg times rs times q oil. Okay, yes.
This formula for RS is for GOR.
It's yes, but is the amount of gas at standard conditions divided by the amount of oil at standard conditions that you get when you vaporize the mixture. Okay.
Yes, because when there's a also that the extra condition that like GOR, gas relation. So I think there is about that solution gas relation that is RS.
Mm-hmm.
So that this RS means GOR, that's the solution gas ratio or only gas ratio.
Well, it's if you see here, it's involving just gas oil ratio, not only solution. If it was just solution, it will be, you'll have to split into how much came. That I'm going to do just now. Okay, just wait a moment. But so RS is just if I have this particular composition. Okay, this part I bring it to surface, and I will get some RS. Okay, I will get the ratio between these two. And I end up with this expression for gas and this expression for oil, BO times QO. Okay, and those are the two we're going to use today in our exercise. And that means that basically the rate at any pressure and temperature of gas is the rate of gas in the surface that I compress. Okay, Bg, remember, is taking into account the compression, and this guy here is taking into account that actually at a certain pressure and temperature the gas can re-vaporize into the liquid. Okay, actually this gas from the surface came from the liquid. One part came because this gas expanded, but one part came because that liquid vaporized. Okay, so that's what actually I'm doing here. I'm saying, well, you in the local conditions you will have, first I have to compress all of this gas, I have to bring it to PNT, and then I have to say, well, maybe part of this gas was back in the oil, so I have to take it away, okay, from this gas. And oil, I don't have that problem. Oil is just BO, because by definition is the ratio between here divided by this guy here. Okay, now to address your question, there is something, if RS is important, okay, then we have to keep track of where surface oil and surface gas is coming from. Okay, we have to keep track. We have to say how much of the oil that I have came from the gas, and this is important for gas condensate reservoirs. Okay, or so gas condensate, wet gas, and also volatile oil. Okay, I have to consider for ARS for these cases. So in that case, I do what you exactly said, that I have gas and I have oil, and then I bring it at a certain pressure and temperature, and then I bring it, and then what I will find is that part of the gas will be, this is gas that comes from gas. Okay, then I have that gas just came by the expansion of the gas. Then I have another gas that came from oil. Okay, and then I have just by the vaporization of oil, and then I have another oil that came from oil, and then I have, let's use switch color this one, and then I have oil that came from gas. Okay, and I have everything that I capture everything. Okay, I have that this guy evaporate first expanded. Also, it might condense some liquid, and this is that liquid. And this guy might vaporize, and also might just you have something that still doesn't vaporize. Okay, and here we have a new definition we have to make, and actually it's is Rs is equal to B of um, it's V of oil that comes from gas divided by V gas that comes from gas, and Rs is V gas that comes from oil divided by V oil that comes from oil. Okay, but we are not going to use that in this course. This just keep it in mind. If you have something like this, gas condensate, waste gas, volatile oil, then you have to include this Rs if you're expecting significant dropout from the gas. Okay, so now that we have this, I will give you an exercise, and you can open it in. It's called example BO properties. Okay, and this is how usually we give black oil properties. We give for a fixed temperature, we give pressure and all the black oil properties. Okay, so I want you to calculate. I have the standard condition rate and I want the local rate, and let's make like two tries. Let's make one assuming that Rs is 0. We just neglect Rs, and let's do another one considering Rs and see how different they are. So here I say, here you can create this matrix, okay, in these squares, and you have to follow the notes. Okay, you have to calculate this term, this term, this term, and this term. Okay, and then you have to multiply that times this vector. And there is a very cool function from Excel called M matrix multiplication. Okay? And with this, you can multiply a matrix times a vector. Okay. So first, calculate each term, and they say please do it for. Want to know the rate at 80 bar at 120. Okay. So you will have to do. I'm not sure if you need interpolation. No, you have 80 here on the table. You calculate these four terms, and then to compute these rates, you just make the matrix, this matrix times this vector. Okay, and do it with Rs and without Rs, and let's see the difference. Okay, so I give you time so you can work. You saw the difference, and basically, so that's a traditional, that's what we call like the traditional, this approach here is called the traditional black oil table definition, BO approach. We make no distinction where the gas is coming from, where the oil is coming from, and we create just these three variables are basically, and it's very simple. Okay, the matrix is reduced considerably. But if in some cases where we have this type of reservoirs or this kind of fluids, then we have to take into account actually, and here I made a mistake. Okay, I said gas that comes from gas, but then that gas is at standard condition. So the bar should be on the first gas, not on the second gas. Okay. And then it makes this matrix a bit more complicated. And remember, when we calculate black oil properties, in this process, we put everything in a piston and we start to expand. Okay. In this one, actually, we will have to take them separately. Okay, because otherwise we cannot know what comes from oil and what comes from gas. So I have actually to take and separate them. Let's make it like another step here. So I come and I separate at standard conditions. I separate and I have the gas, and I have the oil separately, and then I can actually see how much, when I take it to standard conditions, how much gas, liquid is coming from the gas and how much gas is coming from the oil. Okay? And this is a complexity that production engineers have, that we actually have to calculate properties at P and T. Okay, black oil properties. For reservoir engineers, really they take the T out of the equation, and pressure is the only dependence we have. So that's why I don't like to talk about, solution gas oil ratio or formation. I say just BO, BG, RS, and finished. Okay. Let's now make what we had next. What was it? Okay, we're going to make the exercise. Okay, after now that you have been introduced how to calculate local conditions. Okay, so we are going to use. So this is a class exercise, and it's going to be your last home exercise. So it's dp dt calculations in tubing. Okay. And here I have prepared already for you the black oil properties come from correlation. And remember, these properties are basically a function of pressure, function of temperature, are a function of a specific gravity of the oil, are a function of GOR, and they are a function of specific gravity of the gas. Okay, only these three. But you will see now I have included six factors: FO1, FO2, FO3, O4. I think there are six, and these are for tuning the black oil correlations. Okay. For example, you made your experiments, okay, of RS versus pressure, and you obtain, I don't know, these points. And when you apply the correlation, you, for example, obtain these points, okay? And then you can use these factors to try to tune and try to get closer to this line. With these FO factors, okay? We're not going to look into it, but that's actually what you do, because correlations are made they were developed only for a particular group of fluids, either North Sea, California crudes, Middle East, etc. And you always have to tune these correlations so they represent better the measured data. Okay? And reservoir engineers, they know how to do it very well. So, but in this case, we're going to assume that most of them are 1. Okay, so there is no, basically I'm doing no tuning. And we're going to the part, in this calculation, P wellhead pressure is known. And I want to calculate P bottom hole pressure for a rate of oil equal to 1,000 standard barrels per day. And actually, these correlations, they are in field units. So we are going to have to change, because all the rest is in metric, okay, all the pressure drop calculations. So we will have to change from, it will be a bit tricky to do it. But let's go and show you the exercise, and that's the last exercise of the course and the last activity we have for today. Okay, so let's see what we have. First, we have the BO parameters we need, specific gravity of oil, specific gravity of gas, and we have the GOR. Okay, and we have the API that we need, but it's the same as the specific gravity of oil. We have all of these tuning factors that I told you about, and here you have to decide what they are for. One is for the bubble point correlation and for the RS correlation. 2 and 3 are for the BO, and basically this what they do is one of them shifts the curves up and the other one scales the curve. Okay. Then you have 1 for the compressibility of the oil. Then you have 3 for the viscosity. Okay, but all of them are 1. The only one that is not is this one here. Okay, and because I was using it for another field I was working with. So that's the tubing ID. Okay, these are things that we need for the pressure drop calculation. Tubing ID, cross-section area, roughness of the pipe, inclination. Here you have the rate of oil. If you have the rate of oil and the GOR, you're going to get the rate of gas. Okay, wellhead pressure, a wellhead temperature, and reservoir temperature, measure of the fluid. Okay, so I did, the tubing is 3,500 meters long. I divided in every 500 meters. Okay, and I calculated using this linear interpolation temperature in each one of these segments. Okay, 500. Okay, and that's the first pressure we have. Wellhead pressure is 28 bar, and then we have to move, calculate pressure drop, and move here with Euler, calculate pressure drop, and move down with Euler, and so forth. And if you continue dragging here to the right, you have all these black oil properties. You have RS, you have in both units, you have CO, BO, BG, density of the gas, viscosity of the gas, density of oil, viscosity of oil, interfacial tension. And here we have what we need to calculate, the pressure drop. Okay, so that's this part here. It's pressure and temperature conditions, black oil properties from this column all the way to the end, all the way to here. And then here I have all the data I need to calculate this dpdx, okay, to calculate superficial liquid, superficial gas velocities. I need this void fraction from this correlation you have used yesterday, and we have this dpdx. Okay, so it looks complex, but let's try to do it step by step. So I didn't want you to go into the complexity of using the function. You see here the function for black oil has a bunch of things inside. So that I did some homework for you. So for this exercise, if you see, so one of them we have already very clear. Remember, we said dpdx will be minus density of the mixture times sine of theta times g minus, it was 1.5 diameter, friction factor 2 phase, velocity of the mixture squared, and what else? Density, right, of the mixture. I think I'm not missing anything else. Okay, yeah, that's it. Okay, so and we said the density of the mixture will be this void fraction times the density of the gas plus 1 minus the void fraction, the density of the oil. Okay, at local conditions. And this velocity of the mixture will be superficial velocity of the oil plus superficial velocity of the gas. But now, how do I calculate the friction factor? The friction factor, if you remember, we had that plot, okay, that was depending on, we're going to use just the single phase friction factor. And we had, it did something like this, going up and like that, and like that, and like that, etc. And for that, I need a Reynolds, okay, a Reynolds number. The roughness I have, the roughness and the diameter I have, but I need the Reynolds number, that is velocity times density times diameter divided by viscosity. So for density, I'm going to use also the density of the mixture. Velocity, I also am going to use velocity of the mixture. And what about viscosity? Well, I can create also, I'm going to use viscosity of the mixture, that will be E times viscosity of the gas plus 1 minus E viscosity of the oil. Okay, 1 minus E. Okay, and here comes a bit tricky, and this is how where different models differ a bit. Some people say, Well, actually, it's not like that, but I have to take into account which phase is the wetting phase. I have to take into account the flow pattern. Okay, so some people say that's not correct because really we don't have, like, it's not like in the tubing we have one part that is covered with liquid, one part that is covered with gas, one part that is covered with liquid, but actually we might have just, if it's annular flow, we might have everything covered just by liquid. Okay, but if you have any other kind of flow, I have, so that's where the difference comes from. But we are going to use this simple model. Okay, we are going to use this drift flux approach. Okay, so that's everything we need to start our calculations. Yes, so let's see. Okay, we have now, let's go through the steps. Okay, let's go through the steps that we made first in class. You know, it's complex, so we have to go and follow the recipe. First one, discretize the tubing in segments. I have already done it for you. Okay, so you go here, you see we have 1, 2, 3, 4, 5, 6, 7, 8 points, okay, in the tube. Next step, I have to start with the point where the pressure is known. Okay, that is the wellhead pressure. Okay, wellhead pressure is here. Okay. Then the next step says, with pressure and temperature, compute the local rate of oil and gas. But before, there is actually another step. To make that, I have to calculate BO, RS, and BG, right? And then I can calculate these local rates. But I have done it for you already. So you have here BO, BG, and RS. Okay? And then I just have to calculate the local rates that are equal to the expression we just wrote, right? We said Q oil is equal to Q oil times BO, right, at P and T, and Q gas is equal to Q gas at times BG minus Q oil times RS times BG, right? So these are the two expressions we are going to use, and we have everything else. So let's start. QO will be equal to rate of oil at standard conditions, which is constant for the whole tubing blocked, okay, times BO, and BO I have it here to the left, enter. That gives me that the rate was 1000. Then when I'm at a higher pressure, then the rate is 1083, which makes sense. Okay, still some gas vaporized from the oil. Okay, the Q of the gas was equal to the rate of the gas at standard conditions, this guy here, and I'm going to block it, times the BG of that pressure and temperature, BG here, minus the RS times BG, right, times the rate of oil, right? And I freeze that. I hope I didn't make any mistake. Okay, let's see. First we have rate of gas times BG of gas. Okay, that's correct. And that I shouldn't block it because I'm going to drag it down. Minus the RS times BG times the rate of oil at standard conditions, and that one I block. Okay, so it seems like it's correct. Let's see if that expression is correct. Yeah, here it should be not Q gas but Q oil, right? Yes. Hmm? Was that the expression Q oil? Q oil, yes, Q oil times BGRS. Okay, so here we had a mistake, it was Q oil. Yes, you got similar rates? Yes? Okay. So now let's calculate superficial velocities. That's what's going to give me really the pressure drop. Okay, the hold up and the pressure drop. Okay, so I say superficial velocity is just rate divided by the cross-section area of the pipe. Superficial velocity is like if the fluid is traveling all by itself in the pipe. It's occupying everything, all the space in the pipe. So cross-section area, I have it here. And remember to block it. Okay. Why such a big number? Because here this is in days and we have to change to seconds. So we have to divide by 24 times 3600. Q oil, and we can just drag it to the right. It will be the same for Q gas. 4 divided by the area times that. Okay. Now that I have all of that, I can compute what was lambda g. Lambda g was the non-slip volume fraction, okay, the non-slip void fraction. That means rate of the gas divided by the total rate, which is the rate of the oil plus the rate of the gas. That tells me if two phases travel at the same speed, gas will be occupying at the wellhead 80% of the cross-section area of the pipe. So far, so good? Yes. Let's see, just to check, just to, not that I don't believe you, but I will have to check. Cross-section, and you have to change the data. Now go here, and then you have to say fuel oil is just the rate of the sun. Okay, some results of the guidebooks. Yes. Yeah, it's just the rate, if the two phases travel at the same velocity, then it's the rate of gas divided by the total. Yes. So it's gas plus oil. So it's Q gas divided by Q oil plus Q gas. Okay. And that means that gas is occupying 80%. ¿Está bien? Vamos. Okay, now we do exactly what we did yesterday. Okay, to calculate this, we want to calculate the real void fraction. We know that the two phases are not moving at the same speed; they're moving at a different speed, and we have a correlation for that we used yesterday. Okay, so that's called E Wolga. Okay, and remember, this had 8 parameters, so we have to be extremely careful all parameters that it has. So that is superficial velocity of liquid, that would be the oil. Okay, in this case we have only oil. Then superficial velocity of gas, and we don't block because we want to drag it down, and it's going to change depending on the rates. Density of liquid, that's the density of oil, and let's see, we have it here in N16. Okay, density of gas, we have it here in L16. Okay, surface tension, we have it all the way to the end here. What else do we need? We need the angle of the pipe, and the angle it's in C9. We block it. Then pressure of the system. The pressure is all the way to the left. I have it here. And the diameter. Okay, be careful. There are too many parameters. It's very easy to make a mistake. And I freeze the diameter. Okay, gave me 69. Please, one of you check if that's the same number you got. Yes. Yes, 69. What does it mean? Is the gas going quicker or slower than the liquid? Yeah? Slower? Are you sure? If they go at the same speed, the gas will occupy 80%, right? But if now it's occupying less, that means it's going to quick. That's the gas. And yes. you that finished, you can use, try to go and check the function dpdx. Okay, I program that equation that I showed you for you in dpa. It's one function called dpdx. Did you manage? Did you get some dpdx? Okay, so we found something interesting. Okay, the gas is traveling quicker than the liquid. There is slip. Okay, now the last step. At least we are going now to, this is Here we are going to call our multiphase expert, okay, in this dpdx. And we have an expert, and that expert, I programmed that expert for you. That's the last, we know, not the last, but it says compute pressure gradient. Already we have superficial velocity of oil, superficial velocity of gas, and we want to compute the dpdx exactly at that point in the tubing. And for that, we're going to use just this expression, okay? This expression. And I program already for you, so you don't have to do it manually. You have it there in the, okay? So that you call dpdx will be density of the liquid, density of the gas, void fraction, that's epsilon, okay, this E, superficial velocity of liquid, superficial velocity of gas. Let's see, what else do I need? Need a bunch of things. Inclination angle, this one, and I have to block it. Internal diameter of the pipe is C6, I have to block it. Roughness of the pipe, here I have to block it. And the viscosity of the liquid, I go to the left. Viscosity of the oil and the viscosity of the gas, M16, and I got this number. And you have to do quality control. Is that what you also got? Yeah, 267. Okay, bar per meter. How much is, so let's make a very simple quality control. How much is, if you have a column of water, static, how is, if you have 10 meters, what pressure difference you have between top and bottom? Okay, 10 meters of water. How much pressure do you have in 10 meters of water? Or in 1 meter of water. If we put a gauge, okay, we have static just to make, this is just to use QC, okay, quality control. If we have 1 meter, okay, of water, what will be the delta P in this 1 meter of water? Huh? Yeah, the pressure difference in this meter of water, how much will it be? Well, it is density times gravity times the H, right? And that will be, and that's in Pascal, so that will be 1000 times 10 times 1 pascals, and that will be 10,000 pascals, and that will be how many bar? 0.1 bar, right? Yes? Agree or not? Yes, if I put a pressure gauge here, and then I say what will be P1 minus P2, that's what I get, 0.1 bar, right, in 1 meter. So what we are getting here per meter is 0.02. That means 20% of that, which makes kind of sense because you have, 70% of the pipe is filled with gas inside, yes? And we are still not counting the friction losses, okay? You see what I did? Yeah? Repeat. Okay? So if you had a pipe, okay, everything is, you have a meter of this pipe, and everything is filled with water. And you want to calculate the delta P across this pipe. Okay? Delta P is density of the water times the length times gravitational acceleration. That gives you 10 times 1 times 1000. That gives you 10,000 pascals. And you want to divide 10 to the 5 actually pascals is 1 bar. Okay, so actually that gives you 0.1 bar per meter. Okay, and we are getting, from our calculations, we are getting 0.0267. Okay, and we are getting 0.0267 bar per meter, and that means it's like 20% the water. Okay, yes, and that kind of makes sense because the real pipe that we have, the piece of pipe of meter that we have, is really filled only, 70% of it is filled with gas. Okay, 70% is gas, and the gas density is not 1,000, but it's actually, how much is it? If we go here, is 40. Okay, it's much much lower. So it kind of makes sense just to make a quality control. Okay, now next step, what do we have to do? We go to the next step, which was integrate numerically the differential equation. Sounds like a very scary word. Okay, very scary step, but actually it's just using this equation. The pressure of the point below will be the pressure of the point above plus dp dx times the distance between these 2 points. Okay, so let's do it. The pressure below will be the pressure above plus the dp dx times difference between this one minus this one. Okay, I have remembered to put parentheses. It means that the point 500 meters below in the tubing will be at 41.4 bar. Yes? Now I have to repeat everything again, okay, for the next point and the next point. But now remember, Excel is very nice. If we did everything properly with no mistakes, it will be just dragging, right? I can just drag if I make no mistakes, okay? Let's see if Milan didn't make any mistake. We can take all of that line and drag it down, okay? And let's look a bit. So what does it mean here? I have now not 70% but 60% of the pipe of the cross section is occupied by gas. That means maybe I have less gas. Some of the gas is in solution in the liquid. And because I have more liquid, then the pressure drop is higher. It's not 2, but it's 3. Okay? And then I can just drag this guy down. Okay? And I move just like that. Okay? Just dragging this one down. And dragging this guy down. And dragging this guy down. And here I'm doing actually the integration. Okay? This guy down. And I have to use less steps. I'm not sure why I use so many. You see, every time the gas occupies 70%, 60, 50, 40, 30, 20%, and maybe it will be a point where I will find just liquid. And the pressure gradient becomes higher and higher. Okay, drag it down. And actually, at the beginning of the tubing, I just have 5% of gas. So everything it will be like a bubble. Okay, so I will give you time so you can do it yourself. So first, you have to realize we did exactly, we follow the steps one by one. Okay, what I told you, how is the integration? First, the point of pressure that we have, we calculate all properties there, Blackwell properties. We calculate local rates, we calculate densities, viscosities, surface tension, etc. Then we calculate superficial velocities at that point. Remember, that gives me the flow pattern map. That gives me where I'm standing. After that, I use an expert. Okay, in this case, I told you the expert is this equation, simple equation, and this correlation that we used yesterday. You can use any expert you want. You can use any software you want. You can use anything of this big. You have here many things to choose from. Preference is like some people like chocolate, some people like vanilla, some people like strawberry. You choose what you want, what you feel like you like best. Some people they say, okay, if you come to me, you pay this money, I'm a very good expert. And then comes another guy and no, I'm really a better expert. So it depends on who convinced you. Then after that, we said we calculate dpdx and then we integrate. And you can use many methods. In this case, we're using the simplest. Okay, we have pressure at the top. We have delta p dx. We multiply just by the distance, and then we sum it up to that one. And then we just drag it down. Okay, repeat for the next segment, repeat and repeat and repeat. And at the end, we found that the pressure at the bottom of the tubing is 180 something. Okay, 180. Let's see, for something. 183.9, 184. The pressure here, that's the flowing bottom hole pressure that you need to actually to flow against this pressure. 30 was 28, right? 28 bar. And you see the plot actually looks very much, I showed you yesterday, these pressure traverse curves, that they were curved, right? Looks exactly like that, okay? So looks very nice. Now let's see here, you have these two mystical things, the void fraction. Remember, that's actually how much the gas occupies, okay? This epsilon equal to area of the gas divided by area total, okay? For with slip, and this lambda g is just the Q of the gas divided by Q of the oil plus Q of the gas. That's assuming the velocity of the gas is equal to the velocity of the liquid is equal to the velocity of the mixture. Okay? And I have here plotted both, but I didn't put which one is which. So that's bad. Very bad. Legend. Okay, and yeah, that's what you have to deliver for the last exercise. Okay, so you see, so let's look first at the real, okay, the real that is the blue one, okay. So you see it goes from very small 5%, okay, to a value close to 70%. That means probably that here we will have bubble flow, okay, then we go through maybe slug, okay, and then at the end we reach maybe annular flow. Okay, we have all of these three flow patterns here. The model that I chose is not possible to know unless I use a map, okay? But the model that I have, this very simple equation, doesn't tell me what is the flow pattern that I have on the pipe. And you see now, very interesting here, this in this region, okay, below here, the non-slip is actually smaller than the slip. Yes? That means here gas goes slower than the liquid, okay, because gas is only a bubble and then the liquid is flowing around these bubbles, okay. After this point, after this depth from this side, then E is greater than, sorry, it's lower, right, than lambda of the gas, okay. That means that the gas, it goes quicker than the liquid. Okay. The only point where I don't have slip in the tubing is at the depth of um, yeah, 25, maybe 25, 24, 2400 meters. That's the only place where I have homogeneous flow. So I ask you, what happens if I'm using an homogeneous model to calculate pressure drop? I'm going to get everything wrong. Okay, the only point I'm going to get right is this point. All the rest is going to be completely wrong. So you have to, when you have multi-phase flow, you have to take into account the slip of the phases. Okay, extremely important to make a proper prediction of pressure. So I want now, let's see the home exercise that you have to deliver. Okay, you have to deliver exactly what we have done so far, but now you have to also to do a case 2. And case 2, you will say, do the calculations the opposite way. You have PWF equal 200 bar, Q oil, it's again 1,000 standard barrels per day. Okay, and I want to calculate how much is PWH. So I start from the bottom and I have to move up. Okay. Now, one question that maybe you will encounter: what happens if at a certain point the pressure that I calculate here is negative? Okay, for example, here I calculate 100 bar and then plus dp dx times delta x. This gives me a negative number. The next point in the tubing is negative. Is it possible to produce this well or not? No, because I need a much lower pressure. Okay, then in that case I have to increase the bottom hole pressure. But you won't find it because we know this well is able to produce 1,000 if you have 180 right at the at the bottom. Yes. With that, we conclude. Okay. So we talked the first week. We talked about a bit about an overview of how the production system looks like. We said, they're very, you have different systems, but basically you all the time need to test the well. So you need a test separator and you need a production separator. And then you have these routing valves that they decide where to send it. And this causes sometimes a very big cost on it, especially for offshore. Then we went to this very interesting concept of flow equilibrium. Okay, how do you find the operating point? And remember, you have two arms, two curves, one available and one required going up. Okay, you can choose any point you want. You can choose choke, you can use the middle of the tubing, you can choose 100 meters below the Christmas tree. Has to be consistent in every point, any point that you choose. Okay, the equilibrium. And all the time have to look like that. One going like this and one going like that. Then we said, let's go for the case of gas, and we really went in detail for gas. Okay, everything. We covered everything for gas. The tubing equation, we calculate pressure along the tubing. We also calculated for gas. We talked a bit about IPR, and what else? Oh, choke. Okay, we talked about choke. Choke, if the difference in pressure, the ratio between downstream pressure and upstream pressure is less than half, more or less, like a rule of thumb, you have this critical flow, where you have this Mach number 1 in the throat, sonic velocity. Then we talked about liquid. Liquid you already knew, but it's very useful for emulsion, very useful for undersaturated oil. And we saw the effect of temperature that you have actually to discretize to see the effect, how is viscosity changing and density changing along the tubing. And then we talked about the fundamentals of multiphase, the basic definitions of multiphase, and then today, finally, we did an example. How do you integrate with, along the tubing for multiphase? Okay, and that concludes module 2 and 3 of this production, operations, and facilities engineering. Okay, and now I just want to ask you before we close if we can take a picture.